My name is Joshua Jensen with Sunflower Structural Engineering. Today I'm going to cover bolted splices of rectangular plates, and we're going to go ahead and kick this off with an example. We've got two bolts spaced 3 inches apart, used to splice plates as shown below. So this little figure here shows what we're dealing with. We got two bolts, they're just shown with blue circles, and we're going to ignore the friction between the plates. And the example is asking us, what is the shear force in each bolt in this connection? So our design force is over here in this box, and we've got 10,000 inch-pounds of moment, 2,000 pounds of shear, and 1,000 pounds of tension. So the bolt shear from the bending moment can be broken down in this way. So we can start off by saying the moment about the centroid of the bolt group equals the shear force in bolt 1, we're going to call that V1 mx, times the distance away from the centroid, which is 1.5 inches, 3 inches divided by 2, plus the shear force in bolt 2 times the distance away from the centroid of the bolt group, 1.5 inches, which is 3 inches divided by 2. From inspection, we can see that V1 is going to equal V2. They both have the same distance away from the centroid of the bolt group, so therefore their forces are going to be the same in magnitude. So we can go ahead and rearrange this equation here by combining these terms, replacing V2 mx with V1 mx. And so by combining these terms, the 2 in the denominator goes away. And what you're left with is V1 mx times 3 inches. And so we plug in what we know for our moment, 10,000 inch-pounds. I should read inch-pounds, not pounds, equals shear in bolt 1 times 3 inches. We solve for V1. It's 10,000 inch-pounds divided by 3. That's 3,333 pounds. Pretty simple there. And then we're going to do the same thing, but we're going to calculate shear in the bolts from the shear force in the plate. And it's just 2,000 pounds divided by 2. 2,000 pounds is our shear force divided by two bolts. That's 1,000 pounds per bolt. And we're going to do the same thing for our bolt shear. For our axial force, we have 1,000 pounds of axial tension divided by 2 bolts. That's going to equal 500 pounds per bolt. Then we're going to apply Pythagorean theorem to get the resultant shear force. And so for bolt 1, which is the top bolt, the shear induced from bending moment is not additive. It's subtractive from the shear that's induced from the axial tension. So we're going to go ahead and compute the difference between those values and square it. And this 1,000 pounds is from beam shear, which is in the y direction. So for bolt 1, our resultant is 3,004 pounds, and then we do the same thing for bolt 2. Our resultant is going to be 3,961 pounds. Difference between bolt 1 and bolt 2 is that for bolt 2, the shear induced by bending is additive to the shear induced by axial tension. So we're going to add the 3,333 pounds to the 500 pounds. Okay, pretty simple there. So example 2, we're going to get a little bit more complicated here. Find the shear force in bolt 1 from the figure below for an applied moment of 10,000 inch-pounds. 3-inch bolt spacing. We're going to ignore friction. We're going to assume the center of rotation is at the center of the bolt group. We're going to assume a linear elastic response where the magnitude of the shear force induced in a bolt is directly proportional to that bolt's distance from the center of rotation. So if the bolt is 4 inches away from the center of rotation, the shear in that bolt is going to be double what a bolt that is 2 inches away from the center of rotation would have. So we're going to define, here's bolt 1, here's bolt 2, here's bolt 3, here's bolt 4, these blue circles. This red line here is our applied moment, represents our applied moment. This blue line here is our center of rotation. And so these blue arrows here represent our bolt shears. We're gonna say bolt 1, we're gonna call it shear force V1. Bolt 2, we're gonna call it shear force V2, and so on for V3 and V4. And then the distance from the centroid of bolt 1 is going to be called D1. Distance from the centroid of bolt 2 is going to be called D2, and so on for D3 and D4. So we're going to calculate the moment about the center of rotation. Pretty simple. A moment is just a force times the distance. We're going to compute the moment about the center of rotation of the bolt group. So that's V1 times D1 plus V2 times D2 plus V3 times D3 plus V4 times D4. 4 terms, 1 term for each bolt. Because we are assuming a linear elastic response, we can go ahead, because in this equation, this first equation, we have to ask ourselves, what do we know and what do we don't know? Well, we know the moment. We know D1, we know D2, we know D3, we know D4 because we know the bolt spacing is 3 inches. But what we don't know is we don't know V1, V2, V3, and V4. So the linear elastic response is going to allow us to create a mathematical relationship just directly proportional between V1, V2, V3, and V4 to where if we know the shear force in any bolt, we know the shear force in them all. So how you do that is for V2, we can start with V2. You go ahead and you just substitute in for V2. You substitute V1 times D2 over D1. That's all you got to do. Then for V3, you substitute V1 times D3 over D1. And then for V4, you substitute V1 times D4 over D1. You're just taking the ratios of the distances away from the centroid times V1. So now, once you do that, now you've got this whole equation here written out, and the only thing that you don't know is V1. So you can easily go ahead and condense this equation down like this to solve for that. Every term has V1 over D1 in it. So you just pull those out and move them to the front. And it's simply a summation from 1 to 4, since we have 4 bolts, of the distance from the centroid squared. So you can take this equation and we can solve it for V1. So it becomes V1 equals M times D1 divided by the summation of the squares of the distances. So we go ahead and plug in what we know, 10,000 inch-pounds for the moment, plus 3 plus 1.5, that's 4.5 inches for D1. If you look up here, D1, we got a 3-inch bolt spacing, so there to there is going to be 1.5 inches. There to there is 3. 3 plus 1.5 inches equals 4.5. And then we have 4 terms in the denominator of the down here, and we have 1 term for each bolt, and this is the summation of the distances squared. So for bolt 1, the distance is 4.5 inches, and we square that. For bolt 2, the distance is 1.5 inches, we square that. Bolt 3, distance is 1.5 inches, we square that. For bolt 4, the distance is 4.5 inches, we square that. So you solve that equation, and you get 1,000 pounds for V1. Pretty easy. Okay, so the next thing I want to show you isn't an example. It's actually just the general formulas for what we just applied in the first 2 examples. These are much more general formulas, but they're the exact same thing we just did. But instead of breaking it down like we just did, these formulas are already kind of all set up for you. So the shear in any bolt, I, is equal to the moment times the distance away from the centroid, di divided by the summation of the distances squared. That's the core formula we're dealing with here. And then you can separate out the shear force into its x and y components, Pythagorean theorem. You know, and that's convenient because it allows you to add your axial tension and your beam shear to the shear forces that are induced via bending. So it allows you to separate these components out. That way you can add them to the other components. And then at the end, you can find the resultant again. You can bring them all back together again. So the distance squared, the distance, this di, distance from the centroid, that's the x coordinate squared plus the y coordinate squared. That's just Pythagorean theorem, right? So if I'm calculating the distance from the centroid to any bolt, I need to know the distance in the x direction, and I need to know the distance in the y direction. And I take the square root of x squared plus y squared. I get that distance. Now, if you look here, we got x squared plus y squared. There's no square root there like you would see in the Pythagorean theorem. That's because this di here is squared. So this squared term right here cancels out with the square root term, and you're just left with this simpler form here, which is just x squared plus y squared. That's all it is. You gotta do that for every bolt in the group though. And then here's an equation if you just want to get the shear force in the x direction from bending, or if you just want to get the shear force in the y direction from bending. It's the same thing, just set up a little bit differently so you can just get the components that you want. Okay, now these equations will work for any bolt pattern you can dream of. If you've got a bunch of bolts and you know the center of rotation and you know the x and y coordinates of every bolt, then you can apply these equations right here, and these will solve any bolt group for you as far as getting the shear forces for a linear elastic response. But this can be kind of tedious. To get the x squared and the y squared can be a little bit tedious because you got to go through every single bolt. I mean, you just saw in the example we just did how there's a term for every bolt. That can be kind of tedious, right? And when we're designing these things, we don't want to go through and calculate x squared, y squared, you know, and then get to the very end and figure out that, you know, the design doesn't work and we need to go back to square one and try another, you know, try a different spacing or whatever. So if you're just looking at a rectangular bolt pattern that has a consistent spacing between columns, consistent spacing between rows, a set quantity of bolt columns, and a set quantity of bolt rows, if you're just looking at that, which is really a rectangular bolt pattern is very convenient to use. It makes things simple for everybody. You can use these two equations to get your x squared and y squared. So as long as you know your spacing between columns, spacing between rows, quantity of bolt columns, quantity of bolt rows, you can plug those in to these equations and you can get your x squared and y squared, which are the most tedious part of this whole calculation. I mean, you look at this formula here, it's really simple. Other than this di squared, which is simple too, but it's just tedious because you got to go through every bolt. So you can take this equation here and you can just set it up in a spreadsheet, and you know, then you never have to worry about doing this tedious, mundane part of the calculation ever again. These two equations, that's the shear force in the x direction, shear force in the y direction. That's the same thing as these equations right here. The only difference is instead of having this xi here and this yi here, that xi and yi are replaced by qr minus 1 times sr over 2 and qc minus 1 times sc over 2. It's just calculating the distance to the last bolt group from the center of rotation. That's all that is. And so where all these two formulas come from here, um, if you look at the solution of the summation of x squared from 1 to n, or k squared from 1 to n, this formula here, it's 1/3 n cubed plus 1/2 n squared plus 1/6 n. You're just going to apply that you're just applying that to the number of bolt rows. So this k value here, really you can think of that as q, number of bolt rows. You can think of that as qc or qr, number of bolt rows or number of bolt columns. And so you're solving this for q, 1/3 q. So it'd be 1/3 q to the third plus 1/2 q squared plus 1/6 q. Look at this equation right here. 1/3 q squared, 1/2 q squared, 1/6. Now you do have to mess around, and you got to do q minus 1 over 2. You do have to tweak the value a little bit. So that this k value really actually should be q minus 1 over 2. And you're dividing by 2 here, but you make up for it out here at the beginning of the equation. See this 2 factor out here? That's where you make up for that. Okay, so I've shown you these equations for a rectangular bolt pattern. What I've done is I've went ahead and just set these up in an easy spreadsheet, very, very simple spreadsheet for you. And I'll put this spreadsheet on my website, make it available for download. And basically how it works is you've got a section for your design loads. You just got to enter in your moment, your shear, and your axial load in the member. And then you can also enter an allowable shear force per fastener if you want. You don't have to, but if you want. And then you got to enter the quantity of fastener rows, quantity of fastener columns, spacing between fasteners in a row, spacing between fasteners in a column. So you've got 7 inputs, 8 if you want to enter the allowable fastener shear force. And so right here, this section right here, there's 4 equations that are being solved. These equations are just these 4 equations right over here, 1, 2, 3, 4. Yeah, you're just getting the sum of the squares of the distances for a rectangular bolt pattern is all you're doing, and then you're just using that equation there, but you're more using the more specific form for a rectangular bolt pattern. That's what that is there, and that is there. And then it'll go ahead and take the components. It'll split up the forces into components and then find a resultant shear force per fastener for you. So that's how this spreadsheet works. So just to test to make sure this spreadsheet really works, let's test it against our examples real quick. So our first example, we had 10,000 inch-pounds of moment, we had 2,000 pounds of shear, and we had 1,000 pounds of tension. And we had we have 2 rows, and we had 1 column, and our spacing was 3 inches. So if you go down here, it's telling us that our maximum force per fastener, 3,962. So let's go down here and we look, 3,961. 1 pound difference, just a little bit of rounding error there. So that checks out. Now let's check example 2. Example 2, we had 10,000 pounds, 10,000 inch-pounds, of moment. We had 0 shear and 0 axial force. We had 4 rows, 1 column, 3-inch spacing. Come down here, maximum force per fastener, 1,000 pounds. Right here, what we did by hand, we came up with 1,000 pounds. So it checks out. Okay, well, that's all I had for this video. Thanks for checking it out and have a great day.